Okay, welcome back to my YouTube channel, Physics Matters, and a new Geant4 tutorial. In this video, I would like to go further beyond what we have explained last time. So in the last video, I explained how we can create a simple setup for gamma spectroscopy, and we wrote out some of the deposited energy in our terminal. And now I would like to include a possibility to write these information out into a root file, including histogram and also NTuples. But before we do that, I would like to change something else, because we will create really a lot of events, in the order of 100,000. So if we do this within our UI manager with the visualization switched on, we will have the problem that we will run out of memory. I have tried this before and my RAM exceeds and the program crashes. So the best idea is to create a new macro inside our macro folder here, and we can call that, for example, run.mac. And what we can do there is nothing else except initializing our kernel. So we can write here now run number of threads, because we are in multi-thread mode, so we can create more than one thread. So in this case 4, because I have 4 cores in my computer. And then we can write run initialize, for initializing the kernel. And then we can write run beam on, and then 1,000, 10,000, maybe 100,000 events that we want to create. But in order to use this, we have to make a few more changes. We have to go, for example, to our sim.cc, into our main function here, and we have to set this pointer of our UI, G4 UI executive class. We have to set that to 0, or just simply remove that in order to initialize this at a later point. And then what we can also do here, we can go a little bit down below our action initialization, and there we can write if argc equals to 1, then in this case UI should be equal to new G4 UI executive, and then we can hand over our arguments here. So this means that our UI, our G4 UI executive, should only be called if our number of command line arguments in our terminal is equal to 1. If this is not the case, which means that we are actually handing over an additional command line parameter, then it should not open this, and it should just run in batch mode, so to say. And then we have to do one thing more. We have to go actually to our UI manager, and below that you can see that we used here UI manager and apply command, and then we execute our visualization macro. But this should only happen if we are not in batch mode. So we can write here if UI, which means our pointer exists and is not null. Then we can write here, then we can include our function here inside that. And we can also write here UI session start. We can take this from here, remove this, and then place it below that. And if this does not exist, so our pointer is a null pointer, so to say, then we can write here, for example, G4 string command equals control execute, and then we can write here another string, which could be called maybe file name. And this is our first, which means in principle our second command line parameter that we hand over in the terminal. And then we can write here UI manager apply command plus file name. So what happens now is actually that it takes the file name that we hand over as a command line parameter and applies the command control execute, which is the Geant4 command, in order to execute a macro file. So now this is in principle everything which we have to do, and we could now in principle tested already. And here we also have to insert an equal sign, of course. And what we can do now, we can go to our build folder and we can write cmake ... We have to write this because now we created a new macro file and we want to make sure that it's copied to our build folder. So now we can write make, and then it should compile the whole program. I deleted everything again, so we can start now from scratch actually here. And if the compilation is done, we can first try our normal sim command. This works as expected, and we can also create here our events. Yeah, this is perfect. And now we can also write here sim run.mac for macro, and then you can see it creates here a lot of events, yeah, in multi-threaded mode. So we can see here several threads from 0 to 3. Yeah, so we have here 0, 1, 2, and 3, which means that every event is now handed over to a certain thread, yeah, which is quite nice in this case. And here we can also see the energy deposition, and now we have created our 100,000 events. So this seems to work well now. So now in the next step, I would like to create the root files with the histograms and tuples and so on. So the first thing which we have to do, we have to create a new file which is called PM run action, yeah, which handles everything which is done in the beginning of an event or beginning of a run and at the end of a run. So what we can do now, we can create a new file called PM run action.hh as usual. And again, we make our protection here, PM run action _hh, define PM run action _hh, and if. And now we have to include a few things, and we need, of course, our G4 user run action. This is our base class from which we inherit, and we also have to include G4 run.hh. And then the most important thing for our purpose is our G4 analysis manager.hh. And what we also need later is our G4 system of units.hh and our G4 units table.hh. So we can also use units at the end. And if we have done that, then we can create now our class by writing class PM run action, and we have to publicly inherit from G4 user run action. And then we can again create our public environment here with our constructor PM run action and PM run action as our destructor. And then we can create two virtual functions here, and this is begin of run action, and here we have to insert const G4 run as a parameter, otherwise it does not work. So we have to also hand over a pointer to this object, and end of run action is the second function where we have to write again G4 run. And if we have done this correctly and also end with a semicolon, we can see that nothing is underlined, so in principle everything should work. And now we have to go to our source folder, and here we create then of course our PM run action.cc. And this will be a little bit more lengthy, but I think it is very instructive to do it again step by step. So of course we have to include our PM run action.hh, and then we have to define what happens in our constructor. So we write here PM run action, and we can write now, we can keep it empty for the time being maybe, and we define our destructor. So we can write PM run action, and we also keep this empty for the time being. And then we can also define an empty begin of run action, const G4 run. And we can also keep this empty for the time being. And then what we also need is pm run action end of run action const G4 run. And we can also keep this empty because first I would like to test whether we have done any mistake. So I would like to go to our pm action initialization, to our header file. And there I would like to include also our pm run action .hh. And after doing that, then we can go to our source file here, pm action initialization.cc, and we have seen here that we can see that we have already created an object for our generator. And below that, now we can write pm run action, and we can create an object for our run action, which we can call just simply run action. And we write here pm run action, and then set user action run action. So similar to what we have done for the generator, we can also do that for that run action. And then after doing this, we can now write simply cmake ... again, because we have created new files. And then we can run our program, or we can make our program to check whether there's any error message appearing, which seems to be nice. And we can also test it one time whether we get any other kind of segmentation fault, for example, but everything seems to be okay. So we can assume that now this part is also completed. Yeah, and now we really come to the point where we include our analysis manager. So we go to our pm run action.cc that we have just simply created. And then we go to our constructor. So, and here we write G4 analysis manager, and we call that object maybe just simply analysis manager. And this should be equal to G4 analysis manager. And then we can write here instance. So this analysis manager is actually a singleton, and we can create an instance in every function where we want to use our analysis manager. This is really a nice feature. And I think whoever included this in Geant4 has really made it very user-friendly. So now we can write analysis manager create h1, because we want to create now a histogram, and h stands for histogram and 1 stands for 1 dimension. So you can also create 2-dimensional histograms, but here we want to store our deposited energy. So it's enough that we have a simple 1-dimensional histogram, and we can call that maybe edep for deposited energy. This is the name of our histogram, and we can also give a title. So we can write here energy deposit, just energy deposit maybe. And then we can define the number of bins. So let's suppose we want to have 100 bins. We want to start at 0, and we want to go, because we created gammas with up to 1 MeV. So we can write here 1.1 MeV as the upper limit, which means that we have 100 bins from 0 to 1.1 MeV. And in addition to this simple histogram, I would also like to create some NTuples, because we want to store a few more things in our root file. So we can write here analysis manager create NTuple, and we can call that with any name, but let's suppose we just call it photons, because these are the photons information that we want to store. And yeah, then inside this NTuple, we have to then define our columns. So it's like a table actually, and we have to define columns and rows. So we can write here analysis manager create NTuple I column. This is our I stands for integer, and this should be our event number. So we can call that maybe I event. Again, I stands for integer. And then we can continue analysis manager. Now we can create an NTuple D column. D stands for double. Maybe float is also enough in this case, but just to increase the precision a little bit. And then we call that fx, and in this column we want to store the x position of our photon. Yeah, I don't know for which reason we need it, but maybe in the future it could be useful for us. D column, and then we create here column fy. This should be then our y position of the photon. D column, and this should then actually include our z position of the photon. And then we can also maybe write out an tuple D column, the time, and we want to store the global time, which means the time which starts when each event is beginning. Yeah, then it starts counting. So we can write here global time. There's also local time, and the local time only refers to the time of when the particle is created. And then we can create another one maybe, and this should just for fun, we can also write down the wavelength of that photon. We could also write the momentum or the energy, but I think wavelength is also sometimes very nice, especially when it comes to optical photons. Yeah, in case of gammas, it doesn't make so much sense maybe, but just to see what will happen. And then we can also, and then what we have to do, yeah, we have to write now at the end, finish NTuple 0. Yeah, this is important because now it means the definition of our NTuple columns is now completed. Yeah, then we also have to go to our begin of run action, to this function. There we also have to create another instance of our G4 analysis manager. And we can call it, of course, the same. And we will also do exactly the same as we have done before. Yeah, instance, and this should be enough. And then what we can do, we can give this object here a name. So our G4 run, we can call that maybe run. And G4 analysis manager, here I did a typing mistake. And then we can write here G4 int. So we want to create an integer variable, and we call that run ID. And then we can write here run, which we took from this parameter here, and write get run ID. So now we have a unique run ID. And then I would like to include this run ID into the file name of our root file. So what we will do, we will write here std string stream str run ID. So we convert now our integer into a string. This is important in C++. In Python it's not necessary to do that in such a way, but in C++ one has to do it. So we can now write str run ID, and then we can write here analysis manager open file, and then we call that file maybe output. And then we can simply write here plus str run ID dot str. So we convert now this string stream object into a string and add this to our output. And the thing which we have to then, of course, also add in addition is .root. Yeah? So for our first run, we get a file called output0.root. For the second run, we would get output1.root, output2.root, and so on. Yeah, it's not necessary to do that. You could also just simply call it output.root. But it turned out, at least for me in the past, that it is quite useful to create a new output file for every run, because then later you can loop over certain parameters, and then at the end you get different type of files, and you are not deleting or overwriting your previous file. Okay, and then we also have to go to our end of run action, and there we have to create once more another instance of our analysis manager. Yeah, you can also do this globally, of course, for the whole class, but I like to do it like this because then I think it's, first of all, I think it's the recommended way in Geant4, and secondly, it's a little bit better from my point of view to have local objects. It's a little bit easier to handle. Of course, we have to take also care in principle of how to delete this again, but I think because it's a singleton, it's much easier to handle. And yeah, then we can write here G4 analysis manager and again instance. And then we can write here analysis manager write. So now what this function does at the end of each event, at the end of each run, it writes out the file with the NTuples and the histograms. And this is important because if you're not doing that, it doesn't store any information in the files. And then we can write here analysis manager close file. Yeah, so then all open files are then closed. And just for our own idea what is going on, we can just write once more G4 int run ID run and then get run ID. And in order to use this, we have to then also define here our object, which we call again run. And then we can write here G4 cout finishing run. And then we can write here run ID G4 end line, just to make sure that we get a little bit some verbose output, and we know that whenever our run is completed, we will get the line here finishing run and then the run number. Yeah. Okay. In principle, this should be everything, and I hope that we didn't do any mistake. Yeah, and one thing which I forgot to mention, we have to go to our action initialization.cc again. And we have created here our run action within our build, in our build function, but we also have to create it in build for master. Yeah, this is important because our histogram will be created in the master thread, so to say. It will be created in our output 0.root, whereas thread-wise, the output will be then output 0 underscore t0.root, t1.root, and so on. There we will store our NTuples. Yeah, so what we have to do now, we have to write here pm run action, and the same what we have done before, new pm run action, and then set user action run action. It's the same code that we have mentioned here down before, yeah, but we have to also include it in build for master. And now we can test it once more, and we can write here make, and now we can write sim run.macro, and now we can see it runs perfectly fine. Yeah, we don't receive any error message, and we can see that our deposited energy is also given out in the terminal, and we can see here finishing run 0. Yeah, and if we then in the terminal press ls, we should be able to see here our output 0.root. And the reason why we are not seeing the other root files at the moment is because we are not filling anything into our NTuples. So now we could do the following. We could either open this in root. Yeah, so maybe I can do that. And I can, if you have root installed, you can write root output 0.root, and then we can write new t browser, and then what you can see here is our output 0.root, and when we open that, we can see first of all here the definition of our NTuples, which should be all empty as expected, and we should also see here our histogram, the deposited energy, which is also not filled at the moment. Yeah, but we can see that it goes from 0 to 1.1 as we expect. And yeah, we have 0 entries everywhere. The mean value is also 0. So until now, everything is perfectly fine. So now we have to fill it now with life, so to say, and insert a few things. So for that purpose, we go to our PM sensitive detector.hh. Just here in order to include our analysis manager, G4 analysis manager, as we have also done previously. I think we don't need anything else here. And what we also need later is our G4 run manager.hh to get the event number. Yeah, it's also not necessary, but I will just do it in order to have it a little bit more convenient. And I'm showing you the way how I am usually creating my root output. Yeah, you also don't have to do it exactly in the same way, but I think this is quite useful way how to do that. So after doing this, here we don't have to do anything else. We can directly go to our C file, And yeah, there we have to do the following. The first thing which I would like to do in our process hits, yeah, we have to do that. We have to create, I want to create a variable for our event ID because we also want to store that. So we have to write G4 run manager get run manager. Again, we have to get an instance of our run manager, and then we can write here get current event. Yeah, so it gets the event which is currently processed, and then we can write here get event ID. Yeah, so now what it does, it gives us the event ID and stores this in event ID in our variable event ID. And then what we can do in the next step, before we use this, we have to, of course, create our instance of our G4 analysis manager. And again, we call that analysis manager. And we have to create an instance as we have done before. And then we can, we have to get access to the pre-step point actually. So we have to write here G4 step point, and we call that pre-step point. And then we write here a step, the object that we have created previously. And then we can write here get pre-step point. Yeah, so we have a pre-step point in Geant4 and a post-step point. So pre-step points actually includes all information of the first interaction within one step, and the post-step point includes the second or the last interaction of that particle. Yeah, because in every step you have one initial and one one final state of the particle, so to say. So now we want to get information of the pre-step, and then we can write here G4 double. We want to create some more variables, and one is our global time. So just to make sure that we be consistent, we can write here f global time, and then we can write here pre-step point. And this has a function included, which is just, and you can see here actually all the functions that are included. You can get, for example, the mass, you can get global time, you can get kinetic energy, you can get momentum direction, and so on. So we are interested in the global time. So we can write here get global time. And this is in principle everything which we have to do. Now what we can also do is we can create now a G4 3 vector, and this should be our, this we can call pos photon for position of photon. And then we can write here pre-step point get position. Yeah, so this pre-step point also includes information about the position of the particle, and this is a 3 vector, which means we get an x, y, and z position. And the same we can also do for the momentum. So we can write here mom photon for momentum is equal to pre-step point get momentum. And yeah, then we can convert this momentum also in a scalar. So we can write here G4 double mom photon mag. So we will get the magnitude, and again, to be consistent, we can include it like that. And then we can write here equals mom photon dot mag for magnitude. And then in the final step, we can directly calculate the wavelength, WLen, I will call that maybe, or again, we can call it like that. And then we can write here 1 point, and then 2, 3, 9, 8, 4, 1, 9, 3, 9. And this is our conversion factor of the energy of the photon into wavelength. So we can write here now times EV divided by mom fmom photon magnitude. And then what we also have to do, we have to multiply it with 10 to the power 3. Yeah, so we can simply write it in this way. And now we get our photon wavelength as well. Yeah, and then we want to actually store that in our NTuples. So now we have to create a few rows, and so we can write here NTuple I column. We only created one NTuple, so we can write here 0. And we also created only one column. We created several columns, but we want to refer to the first one, which is just called 0. And then here we want to insert our event ID. And now we have to do the same multiple times. Now we have to write fill NTuple D column, yeah, because the second one is the position of the photon. And here again NTuple 0, column 1, and here we insert our photon X position, which is the 0th coordinate of our G43 vector, the first coordinate of course, but it starts counting with 0. And yeah, then the same we can repeat. Analysis manager, fill NTuple D column 0, 1, and then pos photon 1. And then analysis manager, fill NTuple D column 0. Here we have to insert 2. Here we have to insert 3. Pos photon 2, sorry. Okay. Now we have X, Y, Z. And then in the next we can fill again NTuple D column 0 and then 4 global F global time, and then analysis manager, fill NTuple D column 0, 5 F wavelength. Yeah, and then when we have done this, then in the last step, the only thing which we have to do, we have to write at NTuple row. So it means now our row is completed. We have stored all information that we want. Yeah, this means that for every photon that enters our detector, we get a new call of our process hits, which at the end means that for every photon, for every interaction of the photon with our detector, we get a new row, and we can later see that this is correlated to our event ID that we have created before. Yeah, and then we also want to fill in our histogram that we have created before. So in this case, we have to then go to our end of event, because what we want to insert in our histogram is the total deposited energy of this event. And in addition to giving it out in the terminal, we can write now here again G4 analysis manager to create another instance. G4 analysis manager instance, and then what we can write here in addition is analysis manager fill H1. So now we are not filling an NTuple, we are filling a histogram. So we can write now 0. We have only one histogram, so this has the ID 0. This is also very important that we keep the order. Yeah? So if you have multiple histograms, the first one that you create has always the ID 0, the second one has ID 1, and so on. Yeah? In order to not mix it. So if you create a histogram, I would always do it in a systematic order and create a new histogram below the other histogram, so later you don't have to rearrange these IDs. Yeah, and there we then insert our F total energy deposited. So now I think everything seems to be complete and we are ready to test it once more. So again, we can compile everything from scratch. Yeah, and again we can see our graphical output, whether everything works fine. Yeah, so our events are still created, everything is perfect. And then we can create our 100,000 of events, and we can write sim run.mac. And yeah, it is quite fast. If you are doing this with a graphical output, even if it works and it does not crash, it will take a lot of time. But this is quite fast because in batch mode you don't have all these issues of visualization. And yeah, then again, I would like to type ls, and as you can see now here, we have output 0.root. And then we have also T0, T1, T2, and T3. So these thread-wise output files contain the histograms, contain the NTuples, sorry. And this one contains the histogram. So again, we can now first check output 0.root, and we can create a new browser. And then we can see here our histogram again. And we can see mean value 0.6 MeV. This seems to be reasonable. We have a standard deviation of 0.4 MeV, and we have 100,000 entries, so everything seems to be consistent. And then what I would like to do, I would like to write here in draw options hist, and then open this histogram again. And now we can see we have a quite high number of entries, quite large number of entries in one, which makes sense because most of the photons, they just enter our detector and interact with it, make photoelectric effect and lose all the energy at once. So this makes sense. Then we have quite a large amount at 0, which means the photon does not enter our detector at all. Maybe it is absorbed already in the LED plate in front, or maybe it just passes our scintillator without interacting with it. And then, of course, we have quite a few events that are here having different kind of energies. So what we can do, we can right-click here and Z log Y. So now we get a logarithmic Y scale, and we can see that here we have this kind of distribution, which seems to be quite uniform. I'm not sure about the setup, what it actually, whether it makes sense to do it in such a way, but just to show the effect here, which we can get from that. And now we also want to take a look at the NTuples. So we can, for example, open here our output 0 underscore T0, T0.root. And again, we open a new T browser. And now we can see the histogram is not included, but we can only see our NTuples. And we can click on I event. Now we can see the number of photons that are stored inside one event, but we have 100 bins here. Our root browser automatically creates 100 bins, and we have 100,000 events. So what we have here is now actually 1,000 events per bin, but we have sometimes, so what we expect is that we have maybe around 1,000 photons per bin, but what we can see is that we have sometimes 0, sometimes we have quite a small amount, and sometimes we also have a quite large amount. So we can see that in some cases maybe have several interactions of one photon in one event, so to say, or maybe some delta electrons that are creating additional photons which are interacting with the scintillator, and many things can happen. But we can learn a lot from this only by looking at the number of interactions per event. So now we can also take a look at fx. So this is the x coordinate, and we can see most of the photons enter our detector at position 0, which makes sense because we are also shooting them from x equal to 0. And then from y we also expect 0. And then regarding z we get this kind of nice distribution here. So I think most of the photons lose their energy or interact with the scintillator in the beginning when they enter the scintillator, and many of them are just interacting with the scintillator at a larger distance. We also should take a look at the pre-step and post-step and include this in a more precise way maybe to figure out what actually happens. We also should get more information about the type of interaction. Is it content scattering? Is it photoelectric effect? All this we can do maybe at a later stage, but at the end we are more interested in what we can observe with our detector, and this is the energy, the deposited energy per event, and this we can see in our histogram. So these are additional Monte Carlo information that we get here, and we call it Monte Carlo truth, because in a real experiment you would not be able to get these information. You will not be able to see how many photons interact with the detector. You will not get the x, y, z position of the photons, except if you have a detector that has a high granularity and is also divided in bins of x, y, z. And you will also not be able to get information about the global time, just because you don't know when the photon was emitted from the source. So this is also again a Monte Carlo truth information, and the wavelength, of course, you would not be able to get in any case. But it's interesting that now here our wavelength, which should be in nanometer, so this is in the order of maybe 10 picometer, which is I think typical for X-ray and gamma rays. And if you convert 1 MeV into picometer, I think this is exactly the wavelength that you would expect. Yeah, and now let me show you another trick. So Visual Studio Code. If you don't have root installed, you can also use Visual Studio Code in order to display the content of your root files, because there is an extension that you can install, especially for root files. And when you then click here on Build and you open the output file, for example, in this case output0.root, you can see that it displays the same what we have also seen in our T browser. And if we click here on EDEP1, we can see now here our histogram, the same what we have seen before. Yeah, and you can also click here, right click on this axis and then on Z log Y, and then for example log 10. And again, you can see the same results here that we have seen before. And you can also shift this away and then you see the last entry here. And even it gives a little bit more information than root itself. So you can click on certain or highlight certain entries here, and you can get directly information about the energy that is deposited. Now, and maybe we can also make it a little bit larger. And yeah, I think it's a very nice thing. We can also open another one, for example, T0, and there we get information about the NTuples. And again, the same what we have seen before. Here we can see that the binning is different, as well as the events that are shown here on the x-axis. This is something which I also have to find out myself, from where this information is coming and why it changes. But in principle, I think everything works still perfectly well. And here we can also click on FZ, FX, and so on, and we can see the same information that we have also seen before. Yeah. Okay, so in principle, everything works well. And now you can continue with investigating further what kind of things you can write out with the help of this pre-step and post-steps. You can also see what track information you can get and store this in NTuples or in histograms. And by this method, you can now increase slowly the output information which you like to have. Okay, and yeah, again, thank you very much for watching this video and for your attention. I hope that you enjoyed it, that you learned something new. And in any case, I hope that we will also meet again for a new video very soon. Thank you very much for watching this video. If you like the content and want to see more of it, please like and subscribe. And in addition, any kind of support is always appreciated.